Well, having talked about flow and what it actually is, now we'll talk about how we actually measure it. We've got a few fundamental ways we use to measure flow. For example, measuring flow directly, and you could compare this a bit to if you were trying to work out how much flow you had coming out of your tap. One way you could do it is you could fill up a bucket and time how long it took to fill up a bucket. You could tip that bucket out into your swimming pool or whatever it might be, fill up another bucket and time how long it took to fill up that particular bucket. Our positive displacement methods of measuring flow are a little bit like this. We could then measure flow based on mass systems where, well, we've mentioned weighing solids as they move across a conveyor belt or something like that. But more commonly, this is used in a thermal mass sense where we heat up something and we look at how that heat is distributed throughout a system. And then we've got flow, which is another way of measuring flow, which is measuring it based on velocity. And we've got a few different techniques that we can use to measure the velocity. So let's look at that first method of measuring flow, which is our positive displacement one. This is the only one that we're actually looking and directly measuring flow through a device. And you can see we have these oval or elliptical gears. There's a few different shapes that these gears can occur in. And basically they move in a pattern which allows us to move in a set amount of fluid into this particular channel. And then as more fluid comes in, the other gear turns and fluid goes in there and fluid's released from that channel. And so we have this system where we can have fluid coming into one and then fluid coming into the other and fluid coming into the other. This is a lot like that bucket scenario that I was telling you about, that if we have a bucket, we know that bucket's a 20-litre bucket, for example. It takes this amount of time to measure how much water or oil or whatever it is going into that bucket. We can measure flow based on that. Here, we've got a sensor that does essentially the same thing volumetrically. The flow going into there, we can measure and we can connect, for example, an electronic sensor to each of these gears to measure how often these gears are turning around. And based on how often these gears are turning around, we know how much liquid has flown through this system. Each time it flows through, we have a discrete volume of liquid flowing through. Now, to make these, you need pretty tight tolerances and really small clearances so you don't get seepage around these particular gears. We want to capture all the liquid in here. Now, these can work well with a wide different variety of clean liquids, even high viscosity liquids as well. In fact, some of the high viscosity liquids like oils and things can be helpful to actually lubricate these gears and stop them from wearing as much as they would otherwise do. It can work with low flow as well, not just high flow applications. And low flow applications, these gears just turn more slowly. And it might be more suitable for those than, for example, a paddle wheel, which requires a bit of momentum or a decent amount of flow to actually get that wheel to turn in the first place. Now, we could, for example, have a magnetic encoder on these wheels or connect some sort of an encoder shaft to these gears to work out how quickly they're turning and read it into our electronic system. And we do it based on how quickly they're turning. These work pretty well in vibration and noise areas because we're working on the mechanical movement of these particular gears. But we want to make sure we don't put a whole lot of grit in things into these gears. Otherwise, we might damage them and gum them up, and we might reduce the working life of our positive displacement flow meters. We also have thermal flow meters, and there's a few different types of thermal flow meters. In our thermal flow meters, we're basically looking at how much thermal flow we have between some sort of a heating element and the fluid that we're dealing with. And typically, the more material that we have passing past this particular heating element, the more flow of the thermal flow we'll have into that particular liquid or gas. Now, you can see two different types here. There's a few different ways that these can be orientated. One, we might have a heating element with two temperature sensors either side of it. And the more flow that we have, the more temperature differential we'll have between that first temperature sensor that's before the heating element towards the second temperature sensor that's after the heating element. Our other way that we can do it is we can use a hot wire. And essentially, these are often used for internal combustion engine vehicles to measure how much airflow they're coming into their air intake. And in doing so, essentially, we can have a whole lot of air rushing past a wire that we're heating up. Now, the way we heat it up, we put a current through it, and we try and maintain it at a particular temperature. Now, as we have more airflow blowing on it, it's the equivalent of you've probably had some hot food at some point and you blow on it to try and cool it down. The more you blow on it, the more you cool it down. Well, the more air that you've got passing over this hot wire, the more you're cooling that wire down. And to maintain the temperature of that hot wire, you need more current flowing into that hot wire to heat it up again. And so essentially this hot wire style sensor, we're measuring how much current we're using to keep this hot wire at a certain set point of temperature. We have our vortex shedding flow meter. And our vortex shedding flow meter, we essentially put a blunt object, we call it a buff, within the flow of our pipe or our conveying system. And in doing so, we create vortexes, small swirling regions that alternate between high and low pressure regions as a result of this buff that's placed in the way. We can then use a sensor across the pipe, like an ultrasonic sensor, to measure how much of these vortexes there are. And based on the amount of flow that we're having through, and based on the velocity of our flow, we'll have more vortexes generated for our higher velocity flows. Now, these are good because they can give us a linear response, and they're quite robust. You basically stick some stainless steel or something in there. And so they're a fairly low maintenance approach. But remember, what you're doing here is you're actually putting something in your pipe that's actually partially blocking flow. And so that can be a negative for some applications as well. Another way we can measure flow is using a venturi or a differential pressure flow measurement. Basically what we do is we have a pipe that will constrict at one end, either by narrowing the diameter of the pipe or putting some sort of an orifice plate or something that all the liquid or gas needs to pass through. And we measure pressure before and after that point, or before and at that point. And we look at the difference in pressure between the two of these. And this allows us to work out what our fluid velocity is. With an area that's more constricted, we'll have a higher velocity. Now, this is a fairly robust measure once again, but it does actually constrict our flow, which can be detrimental for many applications where we want as much of our fluid flowing through as possible. Now, there's a number of different mechanical flow measurement systems. For example, we can have a little turbine that spins. Think of, instead of one of those big power generators that use wind, a tiny little one that can fit inside the pipe. And the more flow of fluid that you've got through that pipe, the faster that will turn. So you've got turbine systems and paddle wheel systems that do very similar things. And we basically want to measure how fast that little paddle wheel or that turbine or mechanism's turning. And based on how quickly it's turning, we can infer what our velocity of flow is. If our fluids aren't clean, we can have blockages occurring here that would be a very detrimental effect. And we do have wear and tear. We've got all these moving parts here. We also have a minimum flow required to get our turbine or our paddle to actually turn in the first place, so it may not be very accurate or suitable for very low flow applications. We can also use ultrasonics to measure flow, and we've got a few different ways of doing this. One is we use Doppler, where we've probably realized the Doppler effect when a vehicle with a siren is either moving towards us or away from us, and we can work out whether it's moving towards us or away from us based on the change in pitch of the frequency of the siren that's being sounded. Well, we can use that with our little ultrasonic sensor. So we point the ultrasonic sensor tangentially at our pipe we've got liquid flowing through it, and it will bounce off little impurities or maybe air bubbles within that pipe and bounce back. And we receive that, and we use a Doppler effect to work out how quickly, what's the velocity of that liquid that's moving through there. Another way we can do it is we can have an upstream and downstream pair of transmitter and receivers, ultrasonic transmitter and receivers. And we can work out, well, if there's no flow through the device, we should be able to send the time of flight between our upstream one from here to here and our downstream one from here to here should be identical. But as the flow increases, our signal that's traveling with the same direction of flow will have a shorter time of flight, a shorter travel time between our transmitter and receiver. And we can use that to measure or infer, comparing the two of them, what our velocity of our liquid is flowing through there. So there's some real pros to this. For example, we don't need electrically conductive materials flowing through here. We're not blocking our pipes at all. But these can be affected by vibrations, and they tend not to be as accurate as some of our other measures. And we have some materials that pass ultrasonic waves very poorly as well. We also have magnetic flow sensors. These are sometimes called EMF or electromotive force flow sensors. The basic idea behind these magnetic flow sensors, if we have a material that has some electrical conductivity to it, like plain water, not pure water, but water with all the impurities and things in it, it will conduct a small amount of electricity. Now, using Faraday's induction laws, if we have some magnetic transducers, some coils that are producing a magnetic field, and we produce that, or we pass the liquid through the middle of that. Now, at right angles to that, we'll actually generate a small electric field. We can use sensors to measure that electric field, and that electric field will be proportional to how much flow, the velocity of flow of our liquid past those coils producing the magnetic field. It's just like if you've got a motor and the motor's got some magnets in it and some coils, if you turn that motor faster with your hand, you can actually generate like a little dynamo or a generator, you can generate a voltage. And the faster you turn it, the more voltage you can generate. Here we're actually using the electrical conductivity of the material going through this magnetic field and measuring the amount of voltage that's produced from this, which is quite a small amount of voltage. So there's some real pros behind these magnetic sensors. For example, you've got no moving parts, you've got no constriction of flow and nothing in the way there. And it can work for quite dirty, contaminated samples that have some solids mixed in with them that might get caught in some of our other means. But you can't use this for everything. For example, you can't use this for pure water that doesn't have these impurities in it because it's not electrically conductive. And if it's not electrically conductive, it won't generate that voltage as a result of passing through this magnetic field. It also won't work for gas, and it requires a mostly full pipe because you're working it based on the cross-sectional area of this pipe.